Thank you all for joining us here this morning. Hopefully, for any of those, at least in Northeast Wisconsin, I know we've had some bad weather just come through. Hopefully, all of you are safe. I know there was a tornado that touched down, it sounds like, on West Appleton. So hopefully, all of you are okay, or your properties and everything and whatnot are doing good. Thank you for joining us. Really excited to have Ruben here today from Invisia. He is the technical director of AI, and he's going to be sharing his insights and thoughts on building an agent that becomes an expert on any domain. For those of you who are this is joining us for the first time, we do these roundtables every month, except for December. We take December off, but we do a general IT topic every other month, and then on the opposite months, we do a general cybersecurity topic. So feel free to check out our website with the list of events as we schedule those out. I'm also going to put a plug in. We just went live with registration for our annual Fall Tech Summit that will be held on September 30th down in Neenah at the Best Western Premier Bridgewood Resort Hotel. The topic of that is going to be the next IT workforce, how AI is reshaping technology careers, teams, and leadership. And excited that we have Matt Kirchner. If you're familiar with him, he's down in the Milwaukee area. He's the president of ATS Lab Midwest, Mission Learning Systems, and then also hosts the Tech Ed podcast. So I'll put that link in the chat. So if you're interested in learning more, it's a free event to attend. Thanks to our sponsors. And so we'd love to see all of you, or feel free to share the word with any of your colleagues in your networks for that event. But without further ado, I don't want to take any more of Ruben's time, so I'm going to hand it on over to him. And Ruben, they are all yours.
Awesome. Thank you. All right. So I'm going to be talking. Am I sharing anything? No, I am not. Yeah, I'm going to be talking about Sherlock. Sherlock is a agent that we built, and it essentially is built to become a domain expert for just any subject area. We realized we needed to build something like Sherlock because many of our clients have either systems or code bases that no one really knows. So they don't have someone that knows all of the different systems and how they work together. Or there's a scenario where the SME has left and they are stuck with a complex solution that no one really understands anymore. And so there was this need to kind of solve that problem. And so that's why we built Sherlock. And I'm going to talk about how we built Sherlock. And then just in terms of myself, I am, as I was introduced, I'm the technical director at Invisia. I'm also a blogger, and I write about some of the common problems that we face as we build these agentic solutions and how to solve those. And we will provide a white paper on the subject that we're talking about as well. So this presentation was transformed into a white paper that we can share.
And
So
Ruben, I
why
was
do we?
just pop in quick because I forgot to mention, if you do have questions throughout this presentation, anyone, feel free to pop those in the chat. I'll be monitoring that, or feel free to unmute yourself as well throughout this. As Ruben had mentioned to me prior, he likes to make this conversational, if possible, interactive. So at any point in time, you have questions, thoughts, comments, again, either feel free to unmute yourself or pop those in the chat.
So yes, exactly. Thank you. So we covered this a little bit, but why do we need an agentic domain expert? It's because systems can become too complicated to fully understand. And especially now when we have all of these agents that do the coding for us, they tend to produce an awful lot of code. And so your solution, your system is going to become more complicated quite quickly. And I don't think, and it's becoming a challenge to kind of understand, well, what exactly do we have? What did these agents build out? Do we have redundancy now? How messy are things or how clean are things? We need to have some way of understanding what we have and what we've created in combination with these agents that often do the coding for us. Experts are sometimes just completely absent or there are too few. And sometimes, you need to just be able to ask questions without tapping on the subject matter's shoulder, because they're busy and they need to be productive. But you still need to be able to understand how the system works, or you might have some questions that you need answered. We've also seen a lot of companies complain that the analysis and planning phases just take too long, that just coordinating between all of these disparate teams and figuring out how a new feature should be built that might span all of these different systems becomes a complicated task to complete. And this kind of a solution helps with that as well. So the where Sherlock fits in. So I want to talk about a little bit about the kind of the universe of this development process. If you look at this is from the design framework, or this is a framework for the design approach built by the Design Institute, where you have these four quadrants, these two axes. Horizontally, you have the understand, know, and then the making or doing. And then vertically, you have the real at the bottom and the abstract things at the top. And so that you end up with four quadrants. And the understanding, knowing, as well as being real is the facts. So quadrant one is all about facts. Quadrant two is the analysis of those facts and the sense making. And then quadrant three is the ideation or the synthesizing your analysis into new ideas and concepts. And then quadrant four is actually building those things. And then that becomes a new fact for the first quadrant. And that essentially captures the life cycle of the design development process. And where Sherlock fits in at the moment is in quadrant one and quadrant two, and we can kind of go into quadrant three as the next phase. And then with Claude Code and all of these agentic coding solutions, you cover quadrant four as well. So in some ways, AI is plays a part in all four quadrants. But I think that quadrant three is where the human really plays an important role still, and that is the ideation phase, the innovation phase, where you take all of these things and you start to design a new system that does something cool. I think that the human element is still needed there. Any questions? If not, I'll talk about the primary problem in trying to achieve the goal that we previously stated. And that is that a language model in the form of an agent is really still designed as a chatbot. The knowledge that a language model has is the messages, the chat messages that you and the language model have with one another. So the human message and the AI messages are sequenced in a list, and that list is essentially the memory that and the knowledge that language model has access to. In the agentic form, there's two new types of messages that are included in that, and that is the tool call message and the tool response message. So the integration or the ability to give an agent access to tools is provided by those two types of messages. And so the agent then knows that I can call this, get weather tool, and that the parameter that I have to pass is the city. And so the tool call message from the language model says, the get weather app, city New York, and then the agent translates that and passes that request to the right tool. That right tool has a response, and that's the tool message response. And so that becomes then part of the message history that the agent has, and that then covers its knowledge. The issue with that is that there's a token limit. So the first issue is you have a token limit. The language model has a limit to how big that window can be. A token is comparable to a word, although big words can be split up into two or three tokens. So when you're talking about 1 million tokens as the limit, you're perhaps talking about 500,000 words. And a lot of these language models have like 250,000 K token limits. So the amount of information that you can stuff in that in those messages is limited. And so with that, the amount of knowledge that the language model has is also very limited. And with, all of these messages, the language model doesn't really understand, what's an important, what information is important versus not so important. So those are the kind of issues that you have to deal with when you're trying to create an SME, because that SME needs to know a lot more than the million token limit that you have. So there's a couple of techniques to kind of do some context engineering, and context is the all of the messages that you're passing to the model. So that context engineering is what we're going to talk about in this conversation too. So it's going to be primarily centered around that memory limitation. And the other ability that we've given our agents is the ability to learn, not from the training data, because when you're talking about a language model and it was trained on its training material, so those can be trillions of documents that it's trained on. But once that training is over, its knowledge that it has, when all of the weights have been determined, its knowledge is limited to what it was trained on. So it can't learn new things. So again, that learning is something that is, again, a context engineering trick that you create to inject knowledge into those message history and, have it be, and I'm going to talk about how we do that too, where it can learn new things despite that training limitation. Any questions here? Because this is potentially a complex topic. None? Okay, so then I'll talk about the solution. So what we've done then is, instead of focusing on documents, because if you're talking again about a language model and you're passing all of that information to that model, it can read a document, and that document is then becomes part of that message history, the context. The issue with that is, when you read 10, 20, 100 documents, you filled up its memory, and it can't learn anything new anymore, essentially. And within those 100 documents, it also doesn't understand necessarily what's important. It can't see the relationships between concepts that it's read about. So there's a gap in terms of just knowledge, the way we understand things. And so the solution then is to use a graph. A graph database is a relational database where each node is a thing, and then the relationships are the relationships that things have with one another. And so when you look at code, for example, you can take the architecture and you can say, okay, this is an application. This application has a bunch of classes. These classes do things, and you can capture that as a graph, or at least as a tree, a view of how that application is built, from the top level important concepts to the lesser, well, also important functional aspects. But you can also take the relationships between the two. You can see that this function calls this other class's functions. You can also capture that, that the front end is making a call to your back end across this REST API, or you can capture that this class publishes messages and these other ones consume those messages. So you can, through the graph model, capture all of the information that any complex system has. And when you're talking about like solutions, when you're talking about code, it's very much a tree. When you're talking about solutions, it can be a graph. You can have an application A calling an application B, and that application B calling back to application A. So kind of closing that loop. So the graph model is a good representation of how things actually fit together. And the agent, through its graph querying tools, can query that graph and really look at it, depending on what the question is, of course, but it gains an understanding from the top level to the details of what that system can do without having to have everything in its context. So it can query to answer your questions that you may have about what does this system do. It can query the top level nodes and get a basic understanding of the system. And then if you have a more detailed question, it can then traverse that graph and get the details behind that question and is then able to answer that. So that's the one of the ways that we solve this context model is through this graph. And an agent is able to understand these relationships really well because its own internal memory structure, so all of the dimensions, et cetera, that make up the language model's neural network, they're all non-orthogonal. So you don't have a gender dimension and a distance dimension in terms of, the dimensions that it works with, the dimensions of its universe. They're all non-orthogonal. So you have gender to rank or to roles or to whatever. Those types of relationships exist within those dimensions, and the amount of relationships that are captured in one dimensions can be astronomically big. And that helps it understand the nuance in conversation and understands how the world fits together. So the graph models similarly to how its own internal memory structure is. And so then the agent is able to really understand well this whole graph concept and can answer questions efficiently, by traversing those the graph and querying it. The learning capability that we built into Sherlock is there's really two modes. So there's semantic learning. So it's when you have a conversation with the agent, there's a background process that then extracts facts from that conversation. And when there's also experiential. So episodic is like experience, where what we do is we look at the outcome of a conversation, whether you're happy with the results or you're not happy with the results, and then we track it back to the originating request, and we list out all of the things that were done to get from the request to the response, so your response in terms of satisfaction. And then we capture that either as a positive experience or a negative experience. And we inject those experiences into that context window to drive different behaviors from the language model based on past experiences that are related to the topic of conversation. There's actually a ton of engineering involved in doing that, but that creates this ability for the agent to learn from experience and to adjust its behavior over time and essentially to more effectively please the user that is using that system. Now, another element of context engineering is not having just one agent doing all the work, but having multiple agents doing it. So the reason for doing that is you end up needing to have specialists because the amount of tools that are available to the agent can become quite large. And you don't want to stuff it all into one generic agent that then is able to do coding, as well as business analysis, as well as data architecture, as well as being able to route or onboard users. Instead of having one agent, you kind of divide it up into specific roles, and you give each role a specific subset of tools that are related to that role. By having those roles, you can alter the behaviors of the agent too. So I can say, hey, your role is as a developer, and you have to kind of focus your attention to the development tasks versus the data architecture, et cetera. So in doing that, you reduce the amount of context that is injected into the agent because all of those tools and their description are also part of that context. And by specializing, you have less of that per agent type. And then the issue becomes, well, how do they communicate? If the developer needs to do some business analysis, how do they communicate? So that swarm model allows essentially each of these specialists to talk to one another, to ask each other questions, and also to hand off a task to them. So if I start off with the architect and I'm doing some coding related activities, but I have a ontology question and I want to change the schema of my graph, I'm then passed over to Cleo, who's the data architect, to discuss the best way of capturing that new concept in the graph, because I want that graph to be super clean. So I have a dedicated agent that has responsibilities for making sure that that graph structure, the schema, is super clean. And then there's also this developer harness. Any questions so far? Because I feel like I'm racing through this. There's a lot of concepts here, but let me know if there are questions. So revising or kind of coming back to the standard AI agent versus Sherlock. The standard AI agent is simply a language model with that context window. Let me turn the laser on. So it's that the language model with the context, so all of the messages that that you have exchanged with one another. Basic tool integration where the description of the tools is also provided to the language model, and it can pass requests to have those tools invoked, and then it can see the result. So that is your standard agentic model. And then managing that context when the amount of messages exceeds the token limit, you can then you need to kind of do something with that. And oftentimes the first, the oldest messages are simply dropped from the stack. And so then it can forget things that happened many messages ago. With Sherlock, you first of all, you have it's a multi-agent system. You have those same interactions, but then there's this memory processor that extracts all of the interesting information from that conversation and injects those back, as well as having this persistent knowledge graph. So once you've, had it analyze content, your code base, your whatever, and it's in that knowledge graph is always there. The agent always has access to it, and it can always ask questions of it. Okay. So then the issue is, of course, once you have that knowledge graph and you've decided, this is the way that you're going to um, uh, store memory or facts, then the issue is, well, how do you populate that graph? How do you transform code into a graph format? And so there's this job pipelines that we created that essentially reads code and populates the graph. And there's two elements to that code. So the agent creates the jobs, your conversations with the agent. You first define what are the requirements, the specifications for these jobs. How does this framework, this code base fit together? What do I need to look at? Is it Java? Are we using an event-driven system? Are these microservices? What are the dependencies between the system? Are we using dependency injection, for example? Like a lot of those things are needed, the not knowledge is needed for the agent to be able to, build those relationships within your code. So that jobs pipeline is a method that, we can run over and over and over again against the code base to populate or update that graph with new information. So once those jobs are made, they are always there and they can always be rerun. But we realized that just having a language model look at code and populate the graph was actually not a good idea. Language models still have an issue with hallucinations. They are non-deterministic. Code is deterministic. We don't need a language model to interpret code into a graph. We can use tools like Tree Sitter, which is a symbolic tree converter, so it can read code, generate a tree out of that, and then that tree is what is then translated into that graph. So we have a deterministic approach to capturing all of the relationships within code and representing that as a graph. So then we have kind of the skeleton framework for the representation of your code as a graph. And then the job that the LLM then has is to apply meaning to those nodes. So it'll look at code and then provide an interpretation of what is happening in that code that is then also saved with the nodes. And then what we can also do is we can reverse engineer business logic and business requirements and architectural decisions and capture those also. And so there's an enrichment step where we first have a deterministic method of capturing the structure of the code, and then we apply the LLM to provide meaning, intent, business logic, architectural decisions to the nodes in the graph. So when the language model then reads that graph, it not only has access to the structure, but it also has access to the meaning or the intention behind that. And that enrichment process makes that agent just smarter, or at least more knowledgeable about what's going on within your code base. And again, because these are jobs, they can be rerun over and over and over again. And we can, provide best practices and kind of give a basic understanding to the agent of how to build that framework. And so that craftsmanship is also built into the jobs framework engine. We provide the language model with like a manual of best practices and how to solve certain problems. What should it do first? What are the methods of indirection that need to be resolved? We Every step in that job can be tested, so we save the output of that step into our workspace. We save all of the logs. There's a platform of capabilities that the language model has access to. There are manuals for those capabilities so that it understands, to use this platform for that thing, and then that is the input to another thing. And then, so it basically has a manual available to it that is provided to it in a progressive disclosure type of way. So it doesn't need to load up the entire manual all the time. It can look at certain subjects and read those subjects that are relevant to the problem that it's trying to solve, and then solves that, and then uses that knowledge to solve and create create the jobs and the steps in a reliable way that follows best practices. And that harness also has an evaluator, so that evaluator also reads the manuals and understands the best way of solving these problems and evaluates the output of the coding agent and provides it feedback on things to fix. Because a lot of times, these agents take shortcuts. They add requirements that were never there. They just hallucinate requirements. That's a big limitation in terms of development with agents. And so these evaluators, they look for those issues, and then they, fail the job, and then it has to adjust and do it the right way. So that ensures quality. And to be honest with you, this area we're going to heavily refactor because the evaluation framework needs to go into much more detail to get the quality that we want in these jobs. So the job workflow is kind of what I'm showing here, where you see that the execution, so job can run, it can fail, it can be rerun, it can be retried from a certain step. There's a lot going on in this jobs framework that makes it reliable. So anytime that you have a job failure, the agent can then immediately is then notified, and it can look at that job and see what the failure condition was and potentially make updates to that job, and that is then evaluated again, and then it can rerun the job to until it succeeds. So it's kind of like having a person always watching over your system to make sure that that everything runs smoothly. And when there are issues, it can intercept and do something about it right away. And that generally works quite nicely. This actor pattern that we're using as a job runner, if you want to stop a job or you're resetting your cluster or for some reason, State is managed, so it knows where it's at with that job. And when it starts again, it can continue on with that job from where it left off. And those jobs can be run in parallel. So certain steps can be run in parallel. They can be run in sequence. So it's very much a directional agnostic graph model that these jobs run in. And they have multiple failure scenarios, or this is like the state diagram for that job where it ends up being completed. And that the goal here always is to populate that graph with idempotent and updated information. And now we're going to get into that whole learning framework. Any questions so far? Because I'm kind of racing through this. Can we pause here? Is that a good place to pause to kind of capture some questions or
Any
is
thoughts,
anyone
questions, comments from anyone?
not? Okay. I'll continue on from with this part in the chat. There's a couple of no? Okay. How long did it take to construct? Yeah, so to build this system, I was reliant on, I did use Claude Code quite a bit to build this. So Claude is my coding partner, but one person in 3 months or so is able to capture or develop quite a bit of this. This learning framework that I'm going to talk about took me 6 months of coding, but that was before Claude was really, really good. So if I had to do this again, it would probably take a shorter amount of time. So all in all, probably about 9 months. You could probably do it in half a year as an experienced coder, leaning heavily on an agentic coding partner like Claude. You could probably do this in 6 months. This learning from experience was complicated. And one of the reasons that it is complicated is because when you're talking to an agent, when you're having a conversation with anyone really, you're oftentimes jumping from one subject to another. You could be talking about creating jobs and then maybe have questions about the graph. You could be chatting about new ideas that you might have. So it isn't always a smooth experience extracting topical sequences of messages that are about, the same thing. When you're talking about jobs and you want to extract an experience that is related to developing jobs, you want the messages to be about that. And if you want to talk about, the analysis of the graph and, extracting architectural components, etc., or creating documentation that documents the requirements or the business logic that is captured in this solution, that is another job. And those intermixings make uh, experiential learning more complicated. So to kind of solve this, we leaned heavily on natural language processors like Spacey and Roberta. Roberta we used for sentiment analysis, so to capture if the user is happy or unhappy with the result. We use Roberta, and Roberta is trained on Twitter data. So it has a rich training set of interactions that it was tuned towards. And so it's pretty reliable in capturing sentiment. And then Spacey, what it does is it looks more at like what the subject of the conversation is. What if the request is a command or a question or just a response or that type of thing. It does more grammatical identification of the conversation itself. And so using that, you can kind of group together boundaries around conversations because that's the hard part. You want to, so in a whole thread, we want to capture certain boundaries, like what is a conversation, what are the topical boundaries within that conversation, and then grouping those together and flushing from that the episodes that you can convert into an experience. And the shape of that experience is this model of using an observation, and then the thoughts, the actions that led to the result. And then the result is whether or not what the output of or the outcome of that those actions were, and whether they were good or bad. And then we don't bother with the unimportant chatter, that you sometimes have. This is more about how if I've taken a certain amount of steps, can I learn something from that? Did those steps end up producing the right results? And if they did, then the next time that I cover that subject, I'm going to try and repeat that. And if it ended up with a bad experience, I'm going to avoid that. And so what this is interesting in a way, because how you capture these experiences, you can also say, well, you know what? I'm just going to capture bad experiences. I'm not going to capture what was good. I'm just going to capture all of the things that were not good, because I want to focus on innovation. And who knows if there's going to be a better way to do something. So when the agent has figured out, this is a good way of doing something, and you inject that into memory, the next time it's going to try and do that same thing. Well, what if that same thing isn't the best way of doing something? Maybe there's a better way. So by capturing just the negative space, it leaves the positive space kind of open. And each time that it tries to solve a problem by avoiding that negative interactions, you can maybe, find a really novel way of doing something new in that results in a positive outcome. So this kind of learning from experience model, it allows you to do a lot of variations in terms of how you apply those learnings to future experiences. Um, okay, so the next, it's not moving. There you go. So that active context management. So here I'm talking more about, okay, so we talked about the context and how all of that you have a limited context of 1 million tokens. And the cost, let's also talk about cost, right? Because when you're talking about passing 1 million tokens to a language model, so you're maximizing the cost of that model too. 1 million tokens for Claude, Sonnet is $3 per million per request. So every time you send those 1 million tokens to the language model, you're paying $3. And if you're using Opus, I think it's $15. So your costs accumulate rapidly. So you want to minimize and optimize your token usage. You really want this context to be focused on the problem that you're dealing with now. Your last conversation, your last message, or the last couple of messages to that language model really captures the problem that you're trying to solve, or the answer that you need the language model to answer immediately. So really your context window should be tuned to that. It shouldn't be tuned to a long history of many conversations, most of which may not be at all related to what you're trying to solve for now. And you're paying all of that money for tokens that are not at all related or not relevant to the problem you're trying to solve for. So by having this active context management, you're always tuning the context window to the problem that you're trying to solve for. And we do that, and this can be optimized further as well, but we do that by essentially using the same concept we talked about, that topic. We capture the topic of the conversation that you're having now, um, leaving messages that are related to that topic in the context window up to a certain point. We create a summary message of all of the past messages, and we capture those as a summary, and we inject those after the system prompts. The system prompt describes the agent's roles and responsibilities and how it does things, all of the tools that it has access to. So you don't want to touch that. But then we have a summary message that captures the history, the previous history of conversations, and then the relevant topical messages that are being discussed right now. And then we inject the memory messages. So those semantic and episodic memories are injected right before your last message that you're sending to the language model. So then the context of this stack is all related to the subject that you're talking about. So now you're minimizing your cost. The agent is focused on the problem that you're asking it to solve, and therefore the response becomes relevant to that. And you create a better, how do you say it, a more focused agent that is tuned to paying attention to you. And then when you consider that those memory messages also have all of the positive and negative experiential outcomes from previous conversations, then it's even more focused on, a successful solution to the thing that you're talking about. And that's kind of the benefit of having this active context management. But that's some heavy context engineering that we're talking about here. And so it's kind of to show how that memory is injected into an active session, I have here an example of where a memory was injected. And so the observation was that it designed a dependency injection resolution fix for an extraction job without first reading the job frameworks of that manual. It didn't read it, and therefore it had a bad outcome. So then in the chat with that agent, it says to me, before I design anything, let me read the mandatory instructions first, because I learned that lesson the hard way previously, right? And so that's how it applies that memory in conversation. So it refers to a past experience and adjusts its behavior to have a better outcome. Yeah, and so, what did we learn from this? We learned quite a bit. One is that autonomy, um, you really we have not achieved any form of autonomy for the agent. In terms of goals, the goals need to come from the user. Now, the next phase of this is an onboarding harness that will be kind of an interactive session between user and agent to kind of develop, well, what do you want to achieve? Um, and then um, and then to ask some related questions to get a better understanding of what your goals are and what the agent has to do for you in order to create that graph, in order to become that subject matter expert. There's going to be an onboarding harness that is interactive with the user, and that then explains everything that you as a user want that agent to become a subject matter on. A cost, we have blown a lot of dollars on tokens. And cost management has, a lot of that context engineering that I talked about is really to optimize around cost, both to minimize the amount of tokens that we're passing to the agents, but then we are also using caching. So all of these language models have a caching capability. You pay a little bit more to update a cache, but then retrieval from that cache is 10% of the normal cost. So I might pay an extra 20% tax to update cache, but then my retrieval is only 10% of the cost. So you end up winning. And by applying aggressive caching to all of our conversations, we end up with reducing the cost by 80 to 90% of what it used to be. So if I spent, 10,000 in the past on ingesting or becoming an SME on a large code base, I might spend only 2,000 today. The reality is that in a different in the we just spent a couple of $100, about $500 on ingesting a large code base that we had built for one of our clients. And so normally speaking, that would have probably cost closer to 5,000 or $4,000 in the past. So those cost benefits are really there. The amount of the tools that we have are also tuned to token usage. So when I say, hey, agent, read a document, I don't allow it to read the entire document all at once. It can read the first 100 lines of that document and then, progressively read the rest of it. Because sometimes these documents can be enormous. And I've had experiences where just reading one document filled up the entire, million context window. And the document wasn't even that important. So, that is also a waste of tokens. So, and then also directory traversal in order to search for files and things like that in any complex solution, those directories are enormous. And just searching for directories can fill up a context window, and none of that is really relevant. So, there's a lot of tricks and tips that you can apply to minimize your cost. The guardrails, the hard-won guardrails, again, the ontology governance, it's very, very important to have a very, very clean um, database. The schema that captures your graph needs to be well defined. You don't want a mess where you have different node types that are essentially the same thing, because then that just causes confusion. The agent will query for one node type, but the information is in a similar node type, but it missed that because it forgot about those nodes as well. So then, you end up with partial information. You don't want to have that. You want to have a very clean architecture or definition of your schema so that the agent knows what to look for. When it looks for code, you want to have one node type that captures code-related information. Requirements, the same thing. So you want to have a very clean graph. The evaluator framework, again, those are concepts that we will spend a lot more time and energy on because, these coding agents produce an awful lot of code. Sometimes it's just too much to kind of review yourself. So you need help. And having an evaluator framework, assess quality, assess whether or not the agent achieved the goals is going to be extremely helpful, is already helpful, but we're going to expand those capabilities. And then, of course, having the human in the loop. Ultimately, the human is the best, has the best judgment, um, and needs to approve of or give direction to the agents, has to look at results and validate that goals have been met. The human is still very, very much an important element of this whole journey. So that kind of is the end of the presentation. I think I pretty much raced through it. I don't know what we are on time. We did okay, 120. So we have 10 minutes for questions. Because that kind of brings us to the end. So thank you
Yes,
very
you
much.
did great, Ruben, on time there. Awesome. Any thoughts, questions, comments?
Just a comment on my side. I just want to say thank you. It's very inspirational. I have been doing some work almost along the same lines, and I was kind of refreshing to see that even some of the terminology you're using is where I was heading. Currently, I just have this is the first stage of what I'm planning to do. Is I have an MCP-based memory server, and one of the things I found out soon into it is that memory in itself is not. It only takes you so far.
Yeah.
Injecting that into the context is the next step. Is what I'm working on now.
Yeah.
Primarily on using Claude with hooks.
Nice.
But my initial goal is to build, mostly for fun, to build my own agent. So this is very inspirational. So thank you.
Yeah, and I can share the white paper, and everything that I've discussed is in that white paper. And you can kind of follow that along. My blog also talks about it in more detail. So you can kind of, get some information from how things were built. Um, and I hope that, you succeed and get that solution working the way you want it to.
Oh, thank
Because,
you. Yeah, I'll definitely look at that.
yeah, yeah, awesome. And use a graph if you can. That the graph combination with agent is just phenomenal. Um,
Hmm.
it's so powerful. It's incredible.
Excellent.
Thank you, Roberto. Anyone else? Otherwise, any final thoughts or words of wisdom, Ruben, that you want to instill on everyone?
Yeah, certainly. One of the interesting um, things that I've seen, observed about working on something like this is that the more and more I work with these language models, the more I end up doing deterministically. And I'm relying less and less on the language models to develop things. Now, I'm, you know, and the reason for that is the hallucination problem. And a lot of so what I'll end up doing is I'll tackle a problem. I won't quite know how to solve that problem. So there's a lot of interactions with the language model, and then we work on something and we build out something. And then and I see then the limitations of what I've built, what we've built. And I end up, and so then there's a lot of iterations to kind of resolve those issues before I finally have something that's reliable. But when you're capturing, so the interesting thing about Sherlock and using and looking at code is that the facts that I need to have in a graph need to accurately represent the code that I have. So quality is really, really, really important. And quality is really, really hard to achieve with these agents because they have their own interpretation of your request. They add requirements, they take shortcuts. When you're looking at legacy code, for example, apparently, its training data is primarily focused on modern code frameworks. Because when you're looking at COBOL or the old VB6 stuff or whatever, it struggles with that. It struggles to understand that the code, and it takes an enormous amount of shortcuts to achieve success. So these language models have been trained to make you happy, and they will be deceptive in how they make you happy. They will claim success when you don't have success. They will take shortcuts. If you're testing the quality of your graph by looking at how connected it is, it'll create ghost nodes and connect everything to it to kind of show a connected graph, even though it's not actually connected to relevant in things. So there's a lot of shortcuts that they apply to kind of trick you into believing or to kind of be able to say, yes, I've succeeded at something when really it hasn't. So and that's why that evaluative framework is so important, because you're not going to be able to find all of these little things, little gotchas that you've experienced. And so ultimately, when I have an understanding of what I want and how to solve a problem, I put that into that platform and allow the agent to use that component to create a graph, for example, of code, which I know is almost always the same, regardless of the language. The kind of graph that I want to capture from a code base is similar regardless of the language that I'm analyzing, you know? So I can do that deterministically in my platform. The agent can then use that tool to create that graph. And then where it is, the strengths of the language model is primarily around understanding what the code does and be able to summarize what that code does. The summarization component of a language model is its strength. its ability to understand things is its strength, as long as, right, as long as that language, as long as it really does understand it based on the training data. So, but a graph, once you've translated everything and your graph is solid, that understanding of the graph is always good. Does that help at all? I hope it helps. So when they say, these language models have achieved intelligence, I'm not seeing it. And I work with the best models all day long. And that's all marketing stuff. They are an intelligence. They are definitely an intelligence. It's more of a statistical intelligence. The larger the dimensions or the large parameter models that have like trillions and trillions of parameters, Fable, for example, is really good at connecting the dots. It has a good understanding of nuance, and so um, that's its power, right? Its power is the vast knowledge that it's trained on and be able to put all that knowledge together in a new way. So it is an intelligence, but it's not intelligent in terms of being just to be able to problem solve, especially in areas that it's not sufficiently trained on. And I
I
think,
love it. I would say we got 2 minutes left here. Any final thoughts or questions? Well, I just want to thank you, Ruben, for taking the time out here today on a
absolutely.
Monday. Appreciate it. For sharing your expertise and insights with us. Again, thanks to all of you for attending this afternoon. Great to see all of you, and again, be on the lookout for future roundtables that we have each month and other events that are out on our website. But thanks again. I'll be sharing out this recording, and then as soon as Ruben gets me the white paper that he mentioned, I'll get that out to all of you as well. But thanks so much for attending, and have a good rest of your week. Thank you, Ruben.
Thank you. Bye.